Hello, welcome to Fundamentals of Acoustics. This is the 5th week of this course, and during this week we will learn essentially about two important concepts. The first concept will be related to acoustical power, and to understand this concept we will first revisit the course of the concept of power in context of electrical engineering. So, we will understand how is electrical power measured and defined, and then we will map that understanding to the acoustical world. And the second concept we will learn about will be related to one dimensional waves, but not in Cartesian frame of reference, but essentially in spherical coordinate system. So, that is what we plan to cover this week, and let us start. So, we will start by discussing the concept of power, and so instantaneous so let us call this P as a function of t. So, if we have to consider the realm of electricity, then there is voltage, and this is a real signal for which we can measure to understand what is voltage, and this we can express it as real of complex voltage signal. So, real of V E j omega t. So, please remember that here V, the capital V, is a complex number, it is a complex amplitude, and E j omega t, omega is the angular frequency and t is time. Similarly, a current which can vary with time could be written as real of complex amplitude I E j omega t. So, that is our definition for current. Now, we know that this term can also be written as half of V E j omega t and its complex conjugate, which is V star, and the complex conjugate of E j omega t is minus E j omega t, but with a negative sign. So, this term V E j omega t, its real component is nothing but V E j omega t plus its complex conjugate, which is V star times E minus j omega t. And similarly, I t, which is current, I can also express it as half of I E j omega t plus its conjugate, complex conjugate. So, I star E minus j omega t. Okay. So, let us call this equation 1, and then we define power. So, I define it as capital P, and it can change with time. So, mathematically it is equal to the product of voltage and current. So, what a current is flowing, and as a function of time, if I multiply it by voltage as a function of time, then for each instance of time I get power. And if I use equation 1 in this expression, I get 1/4 of V exponent j omega t plus V star e minus j omega t times I e j omega t plus I minus j omega t. Okay. So, I now expand it. So, I get 1/4 of, so I multiply with this. So, I get V I e to the power of 2 j omega t, and when I multiply the two complex conjugate entities, I get V star I star e minus 2 j omega t, and then when I multiply V e j omega t with I star e minus j omega t, I get V I star, and then I get a fourth term V star I. So, now we realize, so we can say that is my relation for complex power, but then we realize that V times I star plus V star times I, okay. So, is equal to, so what is V times I star is the complex conjugate of V star times I. So, both these terms are complex conjugates of each other. So, when I add up two entities which are complex conjugates of each other, essentially what I will get is twice of real of V I star. Okay. So, we plug this back into our relation for power. So, my relation for power becomes P t equals half of real of V I star plus 1/4 of V I e 2 j omega t plus V star I star e minus 2 j omega t. Now, we again compare this term and this term in the parenthesis, and we note that this term, its complex conjugate is the term encircled in red. A complex number and its complex conjugate, I end up with the real portion of it. So, we can say that V I e to the power of 2 j omega t plus V star I star e to the power of minus 2 j omega t equals twice of real of V I e 2 j omega t. So, once again we plug this relation back into our relationship for power. So, power equals half of real of V I star plus half of real of V I e to the power of 2 j omega t. So, we will call this equation number 2. So, that is equation 2. Now, we make some observations. So, we note that the average, so here V is a constant, it is a complex number, but it is a constant, and I star is also a constant, and if both of these are non-zero, then the first component this will not be equal to 0, right. If V is non-zero, if the magnitude of V is non-zero and I star is non-zero, then the first component, which is half of real of V I star, will not be equal to 0. Now, let us look at the second component. Here V is a constant number, it may be complex, I is a constant number. So, e to the power of 2 j omega t is equal to cosine of twice of omega t plus j sine of 2 omega t. Okay. So, if I plot the cosine term, it is a cyclic function and same is the sine term, and over one entire cycle, which means when omega t twice of omega t is between 0 from 0 to 2 pi radians, over one entire cycle, the average of this e to the power of 2 j omega t will be 0, right. So, for instance, over one cycle cosine omega t is or sine omega t is something like this, and if I take its average, this area will cancel out this area. So, average of this for the sine term is 0 and average of this cosine term is also 0, and V and I are constants. So, the overall average of this term over one cycle is 0. So, we can write it average value equals 0 over one cycle, and however, in the first case average value is not equal to 0 over one cycle. Okay. So, this is our expression for power, this is our expression for power. So, what this relation tells us is that the first term is not equal to 0 and it does not change with time. So, this is basically dissipated power. It is dissipated power, and if the amplitude of voltage and amplitude of current does not change with time, then this dissipated power remains constant with respect to time. And the second component, the average value of this second component over a cycle is 0. So, now let us do an example. So, we have an AC source and the overall circuit of the system is very simple. So, it's this AC source is connected to an external resistor, and we say that this AC source so this is an AC source for voltage is such that the value of voltage is equal to 10 cosine omega t, where omega equals 2 pi f and that equals 2 pi times 60 hertz. So, frequency is 60 hertz. Also R equals 100 ohms. So, our aim is calculate power as a function of time. So, in the relation for power, we have to know V, which is the amplitude of complex voltage, we have to know I star and we have to know omega. So, if I know V, I star and omega and I, then I can calculate the relation for power. So, IT is equal to VT over overall impedance Z and the overall impedance of the circuit is 10 ohms, 100 ohms. So, this is 10 over 100 cosine omega t, and that is equal to 0.1 cosine omega t. Okay. So, complex voltage V t is equal to 10 e to the power of j omega t. And if I take the real of this capital V t, I will get this expression, the real portion of. Similarly, complex current is equal to, so the real current is 0.1 cosine omega t, its complex, in the complex domain it will be 0.1 e to the power of j omega t, right, where omega is equal to 2 pi into 60, yeah. So, 60 is the frequency and the unit of omega will be radians per second. So, 2 pi into 60. So, this means that V, the complex amplitude is equal to 10 volts and I complex is 0.1 amperes, right, and what else do we need, and I star is again 0.1. So, we put all this in equation 1 or equation 2. So, what is equation 2? So, what is equation 2? P t equals half of real of V I star plus half of real of V I e 2 j omega t. So, this equals half of real of 10 into 0.1 plus half of real of 10, I is 0.1 exponent 2 j into 2 pi into 60 t. Okay. So, this equals 0.5 plus 0.5 real of exponent j times 240 pi t, and that equals 0.5 plus 0.5 cosine 240 pi t. So, what does that mean? So that is my power. Okay. This is my power, and this is the dissipated portion and this is the cyclic portion of the power. So, what we are going to do is we are going to plot it. So, the first thing I am going to plot is the term in blue. So, my x axis is time and on the y axis I have P, which in watts. Okay. So, my average dissipated power, actually, okay, the dissipated power is 0.5. So, this is 0.5, this is 1.0, and the cyclic portion is this thing, and its amplitude is half, and it will vary from plus half to minus half, and at time t is equal to 0 its value is half. So, it will vary like this. So, it is a cosine wave, and the sum of both of these terms is going to look like this. So, that is my expression for Pt, and the green line this line is 0.5 cosine 240 by t. That is my. So, what we will do is we will do one more example and then move on to the concept of acoustical power. So, the next example we are going to do is, so this circuit was purely resistive in nature, okay, it was purely resistive in nature. In the next example, we will develop an expression for power which has an inductive component and also a resistive component, and then we will compare the results for this particular system which is purely resistive in nature and a system which has an inductive component also. So, but that particular example we are going to do in the next class, and that pretty much completes our discussion for today. So, I look forward to seeing you tomorrow. Thank you and have a great day. Bye.